Welcome to Lecture 11. This is our final lecture. We're going to talk about the final three sections of this course. Section 7.5 is about indeterminate forms and L'Hopital's rule. Section 7.6 is about inverse trigonometric functions. And section 7.7 is about hyperbolic functions. We'll start by talking about indeterminate forms and L'Hopital's rule. Things like 0 divided by 0 and infinity divided by infinity are not numbers. Instead, we call them indeterminate forms. To study the indeterminate form 0 divided by 0, we have a theorem called L'Hopital's rule. First of all, suppose that f is equal to 0 at a and g is also equal to 0 at a. Suppose that f and g are differentiable close to a. So in other words, for some small number delta, we need f and g to be differentiable between a minus delta and a plus delta. And suppose that g of x is not equal to 0 for all x which is close to a but not at a. Then L'Hopital's rule says that the limit as x tends to a of f of x divided by g of x is equal to the limit as x tends to a of f prime of x divided by g prime of x if the second limit exists. Now, let me just remark that L'Hopital's rule says f prime divided by g prime. It doesn't say the derivative of f divided by g. So don't fall into that trap. And because L'Hopital's rule is named after a Frenchman, the H in L'Hopital is silent. It's not Le Hopital, it's L'Hopital. And we can use L'Hopital's rule for things like this. Find the limit as x tends to 0 of 3x minus sine x divided by x. For this limit, we can't just replace the x by 0 because then we would get the indeterminate form 0 divided by 0, and 0 divided by 0 is not a number. So instead, we're going to use L'Hopital's rule, which I've written in the yellow box at the top of the slide. We're going to differentiate the function on the top. We're going to differentiate 3x minus sine x, and we're going to differentiate the function on the bottom. We're going to differentiate x. And assuming that this limit exists, these two limits will be equal. The derivative of 3x minus sine x, of course, is 3 minus cos x, and the derivative of x is 1. And at this point, it is okay to replace the x by a 0. We would then get 3 minus 1 divided by 1, or 2. So let me just repeat that. As long as we're satisfying the conditions of L'Hopital's rule, when we want to calculate a limit, which would otherwise give us 0 divided by 0, we're allowed to differentiate the function on the top and differentiate the function on the bottom, and the limit will be unchanged. Let's do another example. Find the limit as x tends to 0 of the square root of 1 plus x minus 1 divided by x. Now again, if we just replace the x by a 0, we would get 0 divided by 0, and that's not a number. So instead, we're going to use L'Hopital's rule. L'Hopital's rule says we can differentiate the function on the top and differentiate the function on the bottom, and the limit does not change. So our limit is the same as the limit as x tends to 0 of the derivative of square root of 1 plus x minus 1 divided by the derivative of x. if we put 0 into the function we started with, we get square root of 1 plus 0 minus 1 divided by 0. So on the top we have 1 minus 1, which is 0, and on the bottom we have 0. We do get 0 divided by 0 if we just replace x by 0. And in this case, we're allowed to differentiate the function on top, differentiate the function on the bottom. The derivative of the function on the top is 1 over 2 square root of x plus 1, or 1 plus x, I perhaps should have written. And the derivative of the function on the bottom is just 1. At this point, we can replace the x by 0. Square root of 0 plus 1 is 1. So 1 over 2 divided by 1, or 1/2. Let's do another one. Find the limit as x tends to 0 of the square root of 1 plus x minus 1 minus x over 2 divided by x squared. Again, if we replace every x by 0, and I'll leave it for you to check, we get 0 on the top and we get 0 on the bottom. But 0 divided by 0 is an indeterminate form. So we're going to use L'Hopital's rule. We're going to differentiate the function on the top, and we're going to differentiate the function on the bottom. But what do we have now? If we replace the x's by 0 again, 1 plus 0, 1, minus the square root of 1 is 1. So on the top we have 1/2 minus 1/2, or 0, and on the bottom we have 0. Again, we get 0 divided by 0. So we're going to use L'Hopital's rule a second time. Again, we're going to differentiate the function on the top, and we're going to differentiate the function on the bottom. The derivative of the function on the top is minus 1/4, 1 plus x to the power minus 3 over 2. And of course, the derivative of 2x is just 2. If now we replace the x by 0, then we do not get 0 divided by 0. Now we get minus 1 over 8. In this example, we needed to use L'Hopital's rule 2 times. Let's do another one. The limit as x tends to 0 of x minus sine x over x cubed. That's 0 divided by 0, so we use L'Hopital's rule. We differentiate the function on the top to get 1 minus cos x, and we differentiate the function on the bottom to get 3x squared. That's still 0 divided by 0, so let's use L'Hopital's rule a second time. Then we get sine x on the top and 6x on the bottom. But that's still 0 over 0, so we're going to use L'Hopital's rule a third time. We get cos x on the top and 6 on the bottom. But that's not 0 divided by 0, that's 1 divided by 0, and then we're finished. Now, be careful here. We can only use L'Hopital's rule if we have 0 divided by 0. If we don't have 0 divided by 0, then we can't use this rule. For example, find the limit as x tends to 0 of 1 minus cos x divided by x plus x squared. And I'm going to show you a wrong answer. Something is wrong here. I'm saying that this limit is the same as the limit as x tends to 0 of sine x over 1 plus 2x because I've differentiated the function on top and I've differentiated the function on the bottom. And I'm saying that's the same as the limit as x tends to 0 of cos x over 2. Differentiated again. Derivative of sine is cos. Derivative of 1 plus 2x is 2. Replace the x by 0 and I get a half. This is wrong, but why is this wrong? And the answer is because sine x divided by 1 plus 2x does not give us 0 divided by 0 if we replace the x by 0. We can only use L'Hopital's rule when we have 0 divided by 0. So that means this step, this equal sign, is wrong. The correct answer is that this limit is equal to 0. But I'm going to leave that for you to check. L'Hopital's rule also applies to one-sided limits. For example, if we were trying to calculate the limit as x tends to 0 from the right of sine x over x squared, quickly check what do we get if we replace x by 0? We get 0 divided by 0. We're allowed to use L'Hopital's rule. We can differentiate the function on the top and differentiate the function on the bottom. Cos x divided by 2x. That's not 0 divided by 0. That's 1 divided by 0. So we can't use L'Hopital's rule again. We need to consider this. Cos is always between minus 1 and 1. That's bounded. X gets closer and closer to 0. So 1 divided by x gets closer and closer to infinity. So are we going to plus infinity or minus infinity? And the answer is we're going to plus infinity because we have positive divided by positive. Cos x is positive, 2x is positive, so we're going to plus infinity. And then part B, we can calculate the left-hand limit as x tends to 0 from the left of the same function, sine x over x squared. Because it's 0 over 0, we can use L'Hopital's rule and say that's the same as x tends to 0 from the left of cos x over 2x. Cos x is almost 1. It's very close to 1 if x is close to 0. So we could imagine that actually we have 1 divided by 2x. When x tends to 0 from the left, that's going to get larger and larger, but also more and more negative. So we're going to have the limit is equal to minus infinity. Next, I want to talk about the indeterminate form infinity divided by infinity. And L'Hopital's rule also applies in this case. We could use the same rule in the yellow box if we would otherwise get infinity divided by infinity. Formally, let a be either a real number or infinity or minus infinity. If the limit as x tends to a of f of x is plus or minus infinity, and the limit as x tends to a of g of x is also plus or minus infinity, then just as before, the limit of f divided by g is the same as the limit of f prime divided by g prime, provided that the limit exists. And this theorem is also true for one-sided limits. We could replace x tends to a by x tends to a from the right, or by x tends to a from the left, and the theorem would still be true. Okay, so find the limit as x tends to pi over 2 of sec x divided by 1 plus 10x. Now, note that this is an infinity divided by infinity question, because sec pi over 2 is undefined or is equal to infinity, we could say, and tan pi over 2 is also either undefined or we could say it's equal to infinity. Because sec x and tan x are both discontinuous at pi over 2, we're going to need to consider one-sided limits. So first of all, let's look at the left limit. The limit as x tends to pi over 2 from the left of sec x over 1 plus 10x. We have infinity divided by infinity, so we can use L'Hopital's rule. We can use the formula in the yellow box. This tells us we're allowed to differentiate the function on the top, and we're allowed to differentiate the function on the bottom. The derivative of sec is sec tan, and the derivative of tan is sec squared. Now we can simplify this. Cross out the sec on the top with the squared on the bottom. We get tan divided by sec. But what do these mean? Tan means sine divided by cos, and sec means 1 divided by cos. The cosine terms cancel out, and we just end up with sine x. So we want the limit as x tends to pi over 2 from the left of sine x, and that is equal to 1. We could do exactly the same calculation for a right-hand limit, but I'm going to leave that for you to do. Please check that the right-hand limit, as x tends to pi over 2, of our function sec x over 1 plus 10x is also equal to 1. Because the left-hand limit and the right-hand limit are the same, that means that the limit as x tends to pi over 2 of sec x over 1 plus 10x is equal to 1. Now I want to calculate the limit as x tends to infinity of the natural logarithm of x divided by 2 over the square root of x. If we replace x by infinity, we get ln of infinity, which is infinity on the top, 2 square root of infinity on the bottom, we get infinity on the bottom. This is an infinity divided by infinity question, so we can use L'Hopital's rule. We differentiate ln x to get 1 divided by x, and we differentiate 2 square root of x to get 1 divided by the square root of x. And this we're going to simplify like this. That's the square root of x divided by x, or 1 divided by the square root of x. And what is the limit as x tends to infinity of 1 divided by the square root of x? Of course, that's equal to 0. Another one, the limit as x tends to infinity of e to the power x divided by x squared. Again, this is an infinity divided by infinity question. So we differentiate the function on the top and we differentiate the function on the bottom. The derivative of e to the power x is e to the power x. The derivative of x squared is 2x. Then what do we have? Then we have infinity on the top and we have infinity on the bottom. We need to use L'Hopital's rule a second time. Differentiate e to the power x to get e to the power x. Differentiate 2x to get 2. This is not infinity divided by infinity now. This is infinity divided by 2. So of course now we can see that this limit is equal to infinity. There's two more different indeterminate forms to talk about. Yeah, a number multiplied by infinity is infinite. A number multiplied by a positive number is positive infinity. A negative number multiplied by infinity is infinity. Strictly speaking, we're talking about limits. We're not really multiplying a number by infinity. We're multiplying a number by a function which has the limit infinity. So it's like doing, it's like looking at the function 2x. We let x get bigger and bigger and bigger. 2 times 10, 2 times 100, 2 times 1,000, 2 times a million, 2 times a billion, etc., etc. What's happening to that? The limit is equal to infinity. I want to talk about the indeterminate forms infinity multiplied by 0 and infinity minus infinity. We don't have a L'Hopital's rule for these. We only have L'Hopital's rule for 0 divided by 0 or infinity divided by infinity. So if our problem is giving us either infinity multiplied by 0 or infinity minus infinity, we're going to need to rearrange our problem to either a 0 divided by 0 problem or an infinity divided by infinity problem. For example, find the limit as x tends to infinity of x sine 1 over x. Now, this is an infinity multiplied by 0 problem. The limit of x as x tends to infinity, of course, is infinity. The limit of sine 1 over x as x tends to infinity is 0. So what we need to do is we need to rearrange this. Or in this case, we're going to need to do a substitution. We're going to do the substitution h equal to 1 over x. And if we do this substitution, we're going to change this into a 0 divided by 0 problem. So every x we're going to replace by 1 over h. Instead of x at the start, we have 1 over h. Instead of sine 1 over x, we're going to replace that by sine h. And we then need to talk about what is happening in the limit. If h is equal to 1 over x, and if x tends to infinity, that's the same as saying that h tends to 0 from the right. So instead of the limit we were asked for, we're going to be looking at the limit as h tends to 0 from the right of sine h divided by h. And that's easier because that's a 0 divided by 0 problem. We could use L'Hopital's rule. Differentiate sine to get cos, differentiate h to get 1. And then take the limit and we get the answer 1. But actually, we didn't need to use L'Hopital's rule here because earlier in the course, we've already looked at the limit as h tends to 0 of sine h over h. Okay, so just like when we do substitutions in a definite integral, we need to change everything. We need to change all of the x's to h. X sine 1 over x becomes 1 over h sine h. But we also need to change what we write underneath limit. If x tends to infinity, what does h tend to? Well, h is equal to 1 over x. What happens to 1 over x when x gets bigger and bigger and bigger? 1 over x gets smaller and smaller and smaller. And because we're just dealing with positive numbers, h is tending to 0 from the right. X tends to infinity is the same as h tends to 0 from the right. Next example, find the limit as x tends to 0 from the right of square root of x ln x. This is another infinity multiplied by 0 problem. Well, actually, I should be more precise. This is a 0 multiplied by minus infinity problem, but the idea is the same. This time, we're going to change it into an infinity divided by infinity problem. And we're going to do that like this. Instead of writing multiplied by the square root of x, we're going to write divided by x to the power minus a half. And of course, these are the same. But now we have minus infinity divided by infinity. Forget about the minus sign. This is really infinity divided by infinity. So we can use L'Hopital's rule now. We could differentiate ln x to get x to the power minus 1. And we can differentiate x to the power minus a half to get minus a half x to the power minus 3 over 2. Let's simplify that a little bit. That's minus 2 square root of x. And at that point, we can see that the limit as x tends to 0 from the right of our function must be equal to 0. Find the limit as x tends to 0 of 1 over sine x minus 1 over x. This is an infinity minus infinity problem. We do not have a L'Hopital's rule for infinity minus infinity, so we need to change it somehow. Let me just be a little bit more precise here. If x is tending to 0 from the right, then it's an infinity minus infinity problem. But if x is tending to 0 from the left, then it's a minus infinity plus infinity problem. But we don't need to talk about those details. What we're going to do is we're going to put everything over the same denominator, just rearranging our function a little bit. This is the same as x minus sine x divided by x sine x. Do we have a rule for 0 minus infinity? No, we don't need one because 0 is a number. So 0 minus 0 is just 0. For this example, I've changed it into 0 divided by 0. And we know what to do then. We know that we can use L'Hopital's rule. Differentiate the function on the top, 1 minus cos x. Differentiate the function on the bottom, sine x plus x cos x. But that's still 0 divided by 0. So we use L'Hopital's rule again. Differentiate the function on the top, sine x. Differentiate the function on the bottom, you can check 2 cos x minus x sine x. And then what do we get if we replace x by 0? Then we get 0 on the top and 2 on the bottom. So, of course, the limit is equal to 0. Now, a question for you. Oh, let me go back. How do we get 1 minus cos x over sine x plus x cos x? Using L'Hopital's rule and differentiating the function on the top, and then differentiating the function on the bottom. The derivative of x is 1, the derivative of sine x is cos x, and then using the product rule, the derivative of x sine x is sine x plus x cos x. Now, a question for you. There's 4 calculations here. One of these is correct, and the other 3 are wrong. Which one of these is correct? I can tell you that the correct answer is number 4. Well done to those of you who picked that choice. Some more indeterminate forms or indeterminate powers. 1 to the power infinity, 0 to the power 0, and infinity to the power 0 are not numbers. These are indeterminate forms. We can use this theorem to solve limits like this. Let a be a real number, or a be infinity, or a be minus infinity. If the limit as x tends to a of ln f of x is equal to L, then the limit as x tends to a of f of x is equal to e to the power L. Now, just to explain why this works, remember, if we have a continuous function, and the exponential function is a continuous function, then we can swap the places of the function and the limit. So instead of thinking of this as exponential of limit, we can think of this as limit of exponential function. But then after we've swapped those two things around, we have exponential of ln. Those are inverses of each other, so they will cancel out, and we just end up with limit of f. So that's why it works, and this theorem is also true for one-sided limits if we need it to be. Right. Here's the formula, here's the theorem in the yellow box at the top. Apply L'Hopital's rule to show that the limit as x tends to 0 from the right of 1 plus x to the power 1 over x is equal to e. This is a 1 to the power infinity problem. We're going to use the formula in the yellow box. We're going to let f of x be 1 plus x to the power 1 over x. And then instead of calculating the limit of f, we're instead going to calculate the limit of ln of f. After we found this limit, we'll do e to the power of this limit, and then we'll get the answer that we really want. Let me say that again. First, we're going to calculate the limit as x tends to 0 from the right of ln of f of x. And in step 2, we're going to do e to the power of that number, and that will give us the limit that we really want. So we're looking at ln of f of x. That's ln of 1 plus x to the power 1 over x. The power 1 over x we can take down in front of the ln. That's the same as 1 over x ln of 1 plus x. And we want to calculate the limit as x tends to 0 from the right of this function. But this function would give us 0 divided by 0 if we replace x by 0. So we can use L'Hopital's rule. We can differentiate the function on the top, and we can differentiate the function on the bottom. The limit as x tends to 0 from the right of 1 over 1 plus x divided by 1. But of course, that's now just 1 divided by 1, or 1. So that's step 1 done. Now we know the limit as x tends to 0 from the right of ln of f of x. What we really want is we want the limit of f of x. So by this most recent theorem, the limit that we really want is equal to the exponential of the limit that we've just calculated. So in other words, it's equal to e to the power 1, or e. The next few examples are the same. Instead of calculating the limit that we really want, we're going to calculate the limit of ln of our function, and then we're going to do e to the power of that number. Find the limit as x tends to infinity of x to the power 1 over x. This is an infinity to the power 0 problem. We're going to use the same idea. Instead of calculating this limit, we're going to calculate the limit of ln of x to the power 1 over x, and we're going to use L'Hopital's rule to calculate that. How do we do that? Well, same as last time. Ln of x to the power 1 over x is the same as ln x divided by x, and that would give us infinity divided by infinity if we took the limit of the function on the top and the limit of the function on the bottom. So we can use L'Hopital's rule. 1 over x divided by 1, or 0 divided by 1, or 0. The final step is to calculate e to the power of this number. The limit that we really want is e to the power 0, which of course is 1. The answer to this problem is 1. We could use L'Hopital's rule for 0 divided by 0 or infinity divided by infinity, and that's it. Cauchy's mean value theorem says, well, first of all, suppose f and g are nice functions. More precisely, suppose f and g are continuous on a closed interval, differential on an open interval, and suppose that g prime is not equal to 0 on this open interval. Then there exists a point C between A and B such that f prime of C divided by g prime of C is equal to f of B minus f of A divided by g of B minus g of A. I'm not going to prove this. I'm not going to do any examples using this. You can find the proof in the textbook, but I don't think it's relevant for our lessons. I'm going to move straight on to section 7.6, which is about inverse trigonometric functions. First, let's talk about sine. Sine is not one-to-one. How do we know this? We know this because if we draw a horizontal line, the horizontal line is going to intersect the graph at more than one point. However, if we restrict the domain of sine to only being between minus pi over 2 and pi over 2, then we do have a one-to-one function. We have a function where the domain is the closed interval from minus pi over 2 to pi over 2, and the range is the closed interval from minus 1 to 1. One-to-one functions have inverses. We're going to swap the domain and the range, and we're going to reflect the graph along the line y equal to x. The inverse of sine is called arcsine, or inverse sine of x. This function has domain, closed interval from minus 1 to 1, and it has range, closed interval from minus pi over 2 to pi over 2. We can do the same thing for cos. If we use the domain closed interval from 0 to pi, Then we have a one-to-one function, and one-to-one functions have inverses. The inverse of cos is called arcsine or inverse sine. Sorry, arccos or inverse cos. Formally, arcsine x, y equal to arcsine x, is the number between minus pi over 2 and pi over 2 for which sine y is equal to x, and y equal to arc cos x is the number between 0 and pi for which cos y is equal to x. I want to talk about some identities which involve arcsine and arccosine. Have a look at these two triangles. Let's imagine that the bottoms are connected, so we have triangles. This angle just here is arc cos x, and this green angle is arc cos minus x. If we add these two angles together, green angle plus the orange angle is here, then of course we get pi. So our first identity is that arc cos minus x is equal to pi minus arc cos x. I'll leave that for you to think about. I'm going to move on to looking at this triangle. This angle is arc sine x. Why? Well, look at this little grey triangle at the top. If that angle is theta, and if the length of the hypotenuse is 1, then the height of the triangle must be sine x. Going backwards, if x is equal to sine theta, then theta must be arc sine x. And the other angle in the triangle is arc cos x. For the same idea, looking at this little grey triangle over here, if that angle is called theta, then we can see that the height of the triangle x is the same as cos theta. So if x is cos theta, then theta is equal to arc cos x. What is the sum of angles in a triangle? Of course, the sum of the three angles in a triangle is 180 degrees, or pi. So arc sine x plus arc cos x must be equal to pi over 2. As I've written in grey at the top, just to be careful here, this triangle only proves this rule is true for x between 0 and 1. But if we combine this formula with the previous identity, then we can also prove that it's true between minus 1 and 0. This identity is true for all x between minus 1 and 1. Let's talk about the next 4 trigonometric functions. The graph of tan looks like this. If we restrict the domain to the open interval between minus pi over 2 and pi over 2, then we have a one-to-one function. One-to-one functions have inverses. The graph of arctan looks like this. It's the mirror image of the graph of tan if we put the mirror on the line y equal to x. Cotan looks like this. And if the domain is between 0 and pi, it's 1 to 1. The inverse function is called arccotan. Sec x, the graph looks like this. This time we're going to restrict our domain to the half open interval from 0 to pi over 2 union the half open interval from pi over 2 to pi, because this function is not defined at pi over 2. This function is 1 to 1. It has an inverse. Arcsec has this graph. only one-to-one functions have inverses. So we need to choose the correct domain to make our trigonometric function one-to-one before we can define an inverse of it. And the sixth trigonometric function is cosec. The graph of cosec looks like this. The domain we choose so as to make our function one-to-one is the half open interval from minus pi over 2 to 0 union the half open interval from 0 to pi over 2. Then we have a one-to-one function, and one-to-one functions have inverses. Inverse of cosec is arccosec. Every time we change a function into its inverse, we're going to be swapping the range and the domain. The domain of arccosec is the same as the range of cosec, and the range of arccosec is the same as the domain of cosec. Formally, y equal to arctan x is the number between minus pi over and pi over 2 for which tan y is equal to x, etc. I want to talk about the derivatives of these functions. First, I want to talk about the derivative arcsine x. And let me remind you of a formula from last week. Last week, we saw how to calculate the derivative of an inverse function. The derivative of f inverse is the same as 1 divided by f prime of f inverse of x. We're going to be using the formula in the yellow box with f of x is equal to sine x, and f inverse of x is equal to arcsine x. Then if x is between minus 1 and 1, we can do this. The derivative of arcsine is 1 divided by cos of arcsine x, because the derivative of sine is cos. Now I want to simplify this. And I'm going to use the identity sine squared plus cos squared is equal to 1 to simplify this. That's the same as saying cos squared is equal to 1 minus sine squared, or cos is equal to the square root of 1 minus sine squared. But then look what we have here. We have sine of arcsine, and sine is the inverse of arcsine. So sine squared of arcsine of x is just the same as x squared. Let's write this as a theorem. The derivative of arcsine x is 1 divided by the square root of 1 minus x squared, as long as the absolute value of x is less than 1. We can combine that with the chain rule to say that as long as u is differentiable and the absolute value of u is less than 1, d dx of arcsine u is 1 divided by the square root of 1 minus u squared du dx. That's just the formula in above combined with the chain rule. So for example, using this formula, d dx of arcsine of x squared, here u is equal to x squared. That's 1 over the square root of 1 minus u squared, or 1 over the square root of 1 minus x squared squared, multiplied by du dx, that's d dx of x squared. 2x over the square root of 1 minus x to the power 4. Now let's find the derivative of y is equal to arctan x. So this time we're going to use the yellow formula with f of x is equal to tan x and f inverse of x is arctan x. The derivative of tan is sec squared, so we get 1 over sec squared arctan x. And again, I want to simplify this, and I'm going to simplify it using the formula sec squared is equal to 1 plus tan squared. But then we have tan of arctan of x, and that's just x. So we get 1 over 1 plus x squared. Let me write that as a theorem. The derivative of arctan x is 1 divided by 1 plus x squared. The derivative of y is equal to arcsec x. This time we're going to be doing this a little bit differently. Instead of using the inverse derivative formula, we're going to use implicit differentiation. So let me remind you, for implicit differentiation, we start with our equation. Y is equal to arcsec x. That's the same as sec y is equal to x. And we're going to differentiate both sides with respect to x. So we differentiate the left side and we differentiate the right side. d dx of sec y is equal to d dx of x. On the left, d dx of sec y is the same as d dy of sec y multiplied by dy dx. That's sec y tan y, dy dx. And on the right-hand side, of course, we just get 1. Rearrange that. dy dx is 1 divided by sec y tan y. But I want to simplify this. Remember, we have sec y equal to x. We know that tan y is plus or minus sec squared y minus 1. Why? Because sec squared is equal to 1 plus tan squared. And sec y is x. So that means tan y is plus or minus the square root of x squared minus 1. So far we've got to dy dx is plus or minus 1 over x square root of x squared minus 1. What can we do about the plus or minus sign? We don't want that here. Well, let's have a look at the graph. This is the graph of arcsec, and you can see from the graph that the derivative of arcsec is always positive. So we want to choose the plus or the minus, so this is always positive. More elegantly, we can replace the plus or minus 1 over x by 1 divided by the absolute value of x. And then we will get a function which is always positive. So here's the formula. Here's the theorem. The derivative of arcsec x is 1 divided by the absolute value of x, square root of x squared minus 1, for any x which has absolute value greater than 1. And at this point, it's a good place to take a break before we look at the other three inverse trigonometric functions. Let's take a break until 3:15. And now let's continue. We've done derivatives of 3 of the inverse trigonometric functions. Now we'll look at the other 3. And these 3 are easy to find using these identities. We've seen the first one, arccos x is pi over 2 minus arcsine x. But there's 2 similar identities. Arccotan x is pi over 2 minus arctan x. And arccosec x is pi over 2 minus arcsec x. I've proved the first of these 3. The second 2 can be derived in similar ways. So, for example, we can then easily calculate that the derivative of arccos x is the same as the derivative of pi over 2 minus arcsine x. We know the derivative of arcsine x is in the yellow box at the top. So this is just minus 1 over the square root of 1 minus x squared. Let's just go through them. These first 2 are a pair. The derivative of arcsine is 1 over the square root of 1 minus x squared. And the derivative of arccos is minus that, minus 1 over square root of 1 minus x squared. Tan and cotan are a pair. The derivative of arctan is 1 over 1 plus x squared, and the derivative of arccotan is minus 1 over 1 plus x squared. The derivative of arcsec is 1 over the absolute value of x, square root of x squared minus 1, and the derivative of arccosec x is minus this. Now that we know how to differentiate the inverse trigonometric functions, we then know how to do some integrals. We know that the integral of dx over the square root of a squared minus x squared, well, that looks almost exactly the same as the derivative of arcsine. Doing a substitution, I'll leave it for you to check that this is the same as arcsine x over a plus c. Or the integral of dx over a squared plus x squared, 1 over a arctan x over a plus c. And finally, the derivative of dx over the absolute value of x, square root of x squared minus a squared, is 1 over a arcsec absolute value of x over a plus c. All of these formulae you have on your formula page in the exams. So for example, find the integral from root 2 over 2 to root 3 over 2 of dx over the square root of 1 minus x squared. I've put the formula that we need in the yellow box at the top. We have exactly what we have in the yellow box with a equal to 1. So of course, this is arcsine x calculated at root 3 over 2 and root 2 over 2 is equal to dot 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 is equal to pi over 12. You fill in the missing bits here. Where am I? Find the integral of dx over the square root of 3 minus 4x squared. Right, it's not quite what we have in the yellow box. We need to do a substitution first. We're going to let u be equal to 2x. And then when we do the substitution, I'll leave it for you to check, we get a half integral of du over the square root of 3 minus u squared. And that does look like what we have in the yellow box. Look at the yellow box at the top. we have the same type of thing, and we have a equal to the square root of 3. So this must be a half arcsine of u over a plus c, or a half arcsine of 2x over root 3 plus c. This is just using the formula and doing a little substitution. Find the integral of dx over the square root of e to the power 2x minus 6. Where do we get the half? It comes from this 2 just here. When you do u is equal to 2x, that means du is 2 dx, so a half du is equal to dx. For this example, again, we're going to need to do a substitution. We're going to let u be e to the power x. And then du is du dx dx, e to the power x dx, or u dx. And then we have that dx is du over u. So then when we do this substitution, our integral changes into the integral of du over u square root of u squared minus 6. And that's almost what we have up here in the yellow box. It's not exactly the same because there's absolute value signs up here. But that's not a problem for us because remember, our u is equal to e to the power x, and e to the power x is always positive. So our u is always positive. So don't worry about that. We can use the formula in the yellow box to find that this integral is equal to 1 over a, so that's 1 over root 6, arcsec, absolute value of u divided by root 6, plus c. Or 1 over root 6 arcsec, e to the power x over root 6. We don't need the absolute value signs here because e to the power x is always positive. Find the integral of dx over the square root of 4x minus x squared. Now, this doesn't match any of our integration formulae because none of the integration formula had things like 4x minus x squared in. So first, we're going to need to rewrite this so that it does match one of the formulae. And I'm going to do that by completing the square. X squared minus 4x is the same as x squared minus 4x plus 4 minus 4. Add on a number and subtract the same number, doesn't change. But then we have, in green, x squared minus 4x plus 4, which is the same as x minus 2 squared, and then minus 4. So what we're really doing is the integral of dx divided by the square root of 4 minus x minus 2 squared. And that's not quite what we have in the yellow box at the top, but close to it. We can do a substitution. We can replace x minus 2 by u. And then, of course, du is equal to dx. No changes there. And then we do have something which looks like the formula in the yellow box with a equal to 2. And I'm just going to say equal to dot, dot, dot. I'm going to leave this problem for you to finish. Find the integral of dx over 4x squared plus 4x plus 2. Again, we're going to need to start by completing the square. Here's the calculation. I'll leave it for you to check later. 4x squared plus 4x plus 2 is the same as 2x plus 1 all squared plus 1. So we need to calculate the integral of dx over 2x plus 1 squared plus 1. What does this look like? It looks like the formula in the yellow box. It looks like a half integral of du over u squared plus a. Yes, I know the formula in the yellow box has a first and x second, but it doesn't matter. We now have an integral which looks like the formula in the yellow box. So this must be a half 1 over a arctan u over a plus c. Or for the final answer, a half arctan 2x plus 1 plus c, because of course a is equal to 1. And then that brings me on to the final section of this course. The final topic on the syllabus for this course is hyperbolic functions. The hyperbolic sine and hyperbolic cosine functions are defined using these formulae. Sine x is e to the power x minus e to the power minus x over 2, and cos x is almost the same, but it has a plus instead of a minus sign. Now, if you forget which one is which, try to remember that sine 0 and sine 0 are both equal to 0, and cos 0 and cos 0 are both equal to 1. What do the graphs look like? First of all, hyperbolic sine, the graph looks like this. This is a function with domain and range, the whole real line. How can we pronounce S-I-N-H? Well, there's two common ways to write it, to say it. The way I prefer is to pronounce this as shine. Some people like to say cinch. Use whichever one you prefer. Hyperbolic cosine, or cosh, has this graph. The domain is the whole real line. The range is the closed interval from 1 to infinity. Hyperbolic tangent, or fan, means sine divided by cosh, just as tan means sine divided by cos. We have the same thing for the hyperbolic tangent. And the graph looks like this. The domain is the whole real line, and the range is the open interval from -1 to 1. Instead of doing sine over cosh, we could do cosh over sine to get cof x, or hyperbolic cotangent of x. This function is not defined if x is equal to 0, because we can't divide by 0. And it has the range, open interval from -infinity to -1, union, open interval from 1 to infinity. There's two more. We have hyperbolic secant, or sech x. That means 1 divided by cosh x. And we have hyperbolic cosecant, cosec x. There's various identities for hyperbolic functions. For example, if we calculate cosh squared x minus sine squared x, that should be, there's a mistake there. Just using the definitions, cosh x is e to the power x plus e to the power minus x over 2, and sine x is e to the power x minus e to the power minus x over 2. Multiply all of these terms out, and then most of them will cancel. E to the 2x cancels with minus e to the 2x. E to the minus 2x cancels with minus e to the minus 2x. We're left with 2 plus 2 is 4, divided by 4, or 1. We can prove all of these identities in the same way. We've just done cosh squared x minus sine squared x is equal to 1. Remember, cos squared plus sine squared is equal to 1. Same idea here, but with a minus sign. Sine 2x is 2 sine x cos x, same as for sine and cos. But for the third one, again, we have a sign change. I remind you that for trigonometric functions, cos 2x is cos squared x minus sine squared x. For hyperbolic cosine, cosh 2x is cosh 2x plus sine squared x. Going down, cosh squared x is the same as cosh 2x plus 1 over 2, and sine squared x is cosh 2x minus 1 over 2. Fan squared x is 1 minus sec squared x, and cof squared x is 1 minus cosec squared x. Let's talk about the derivatives and integrals of these hyperbolic functions. The first one is straightforward. The derivative of sine x, well, that's just the derivative of e to the power x minus e to the power minus over 2. And we know how to differentiate e to the power x, and we know how to differentiate e to the power minus x. That's just e to the power x plus e to the power minus x over 2, or cosh x. And the derivative of cosec x, cosec means 1 divided by sine. So we're differentiating 1 divided by sine x. And we can use either the quotient rule or the chain rule to see that that is the same as minus cosh x divided by sine squared x. Or minus 1 over sine x, cosh x over sine x, but that's just the same as, oh, I've missed a minus sign here, minus cosec x, cof x. So let me just tell you the 6 formulae. We've proved 2 of these. The other 4 I'll leave for you to do if you wanted to. The derivative of sine is cosh, and the derivative of cosh is sine. So there's a difference from trigonometric functions, because you know for trigonometric functions the derivative of cos is minus sine, but here we have plus sine. The derivative of fan x is sec squared x, and the derivative of cof x is minus cosec squared x. The derivative of sec x is minus sec fan x, and the derivative of cosec x is minus cosec x cof x. You will have all of these formulae on the exam this semester. If you have to repeat this course next semester, you might not be given these. Next semester, you might have to remember all of these. Let me just remind you of the similar formulae for trigonometric functions. And they're almost the same. There's just two differences. Derivative of cos is minus sine, and the derivative of sec x is plus sec x tan x. But other than that, they're pretty much similar. After we know how to differentiate these things, then we know some integral formulae. If the derivative of cos is sine, that means the integral of sine is cos x plus c. And if the derivative of sine is cos, then the integral of cos must be sine, and so on. The derivative of fan is sec squared, so the integral of sec squared is fan x. Now, these integral formula I will not give you in the final exam because it's basically just the same as the derivative formula. If you understand the derivative formula, then you can use them to write down the integral formula. Let's do some examples. Differentiate fan of the square root of 1 plus t squared. This is just a chain rule question. We have our formula in the yellow box, and we're going to use the chain rule. Sec squared, square root of 1 plus t squared, multiplied by the derivative of 1 plus t squared. So t over root 1 plus t squared, sec squared root 1 plus t squared. If you know the chain rule, then you can do this. Integral of cos 5x dx, that means the integral of cos 5x divided by sine 5x. This is a substitution question. We need to do the substitution. U is equal to sine 5x. And if we do that, our integral simplifies down to 1 over 5 integral of du over u. And this one we did last week. The integral of 1 divided by u is just ln absolute value of u. The integral from 0 to 1 of sine squared x dx. Using the identity, this is the same as the integral from 0 to 1, cos 2x minus 1 over 2 dx. We know how to integrate cos. We know how to integrate 1. We just get sine 2x divided by 2 minus x. In the exam, I might give you something like this. I might say, calculate this integral, and then your final answer would look like this. Your final answer to this question would be sine 2 divided by 4 minus a half. You don't have to get the decimal because you will not have a calculator. And getting the decimal at the end is not impressive. Anybody who has a calculator, a monkey who has a calculator, could get the final answer. Getting the answer in the blue box is the impressive part. There's 2 just here. It comes from the identity that we talked about earlier. We go back to wherever it was. It was before we started doing derivatives, when we were talking about identities. It's this one. The integral from 0 to ln2 of 4 e to the power x sine x. Remember, sine x just means e to the power x minus e to the power minus x over 2. So really, we're just integrating 2 e to the power 2x minus 2. And we know how to do that. So you should be able to finish this yourself. And the final answer would be, well, 4 minus 2 ln 2 minus 1. Actually, the final answer should be 3 minus 2 ln 2. So that's derivatives and integrals of the hyperbolic functions. Now let's talk about the inverses of these. Sine, fan, cos, and cosec are all one-to-one functions, so they all have inverses. Cos and sec are not one-to-one if they're defined on the whole real line. So we're going to need to restrict the domain of these 2 functions before we can define the inverse. Sine is one-to-one. This is the inverse arcsine. For cos, we need to restrict the domain to the closed interval from 0 to infinity. And then we have a one-to-one function, which then has an inverse. Arccos has domain closed interval from 1 to infinity and range closed interval from 0 to infinity. Because the domain of arccos is the same as the range of cos, and the range of arccos is the same as the domain of cos. When we do an inverse of a function, we swap the range and the domain. Fan is a one-to-one function, so it has an inverse. Cof is one-to-one on its domain. Its domain is all of the real line except 0. Hyperbolic functions are not the same as parabolic functions. So we go back. These are, it might look similar to the bit I've shown, but if I drew them both on the same axis, you will see that, let's say e to the power x, it looks like this. Whereas this one goes up to infinity much, much quicker. The shape is quite different. Try it. Try going to a website which can draw graphs. Google can do it. Wolfram Alpha can do it. And try plotting y equal to cos x and y equal to x squared, and you'll see the difference. Do we have to draw graphs in the final exam? I might ask a graph drawing problem, but it would be the same style of question that I asked on midterm 2. So it would be a rational function. For these slides, just understand the rough shape of these functions. Now, where was I? Sech is not one-to-one on the whole real line, but if we restrict the domain to the closed interval from 0 to infinity, then it is one-to-one. So then we can talk about its inverse. And cosec sech is 1 on its domain, so it has an inverse. Let's talk about some useful identities here. Sech of cosh inverse of 1 over x. Remember, sech means 1 divided by cosh. So this is 1 divided by cosh of cosh inverse of 1 over x. Cosh and cosh inverse, of course, are inverses of each other, so they cancel out. We just get 1 divided by 1 over x, or x. If we then take inverse sech, or arcsec, of both sides, then we get inverse cosh of 1 over x is inverse sech of x. And there's 2 more formulae, which I'm not going to prove. Inverse cosec x is inverse sine of 1 over x, and inverse cof x is inverse fan of 1 over x. Another one, and this one is not in your textbook. Next, I want to find a formula for arcsine x, or inverse sine of x. And I'm going to do it like this. I'm starting with inverse sine of x is y, or that's the same as saying x is equal to sine of y. But sine of y is just e to the power y minus e to the power minus y over 2. So 2x is e to the power y minus e to the power minus y. Multiply everything by e to the power y. 2x e to the power y is equal to e to the power y squared minus 1. Or rearrange that, that's the same as 0 is equal to e to the power y squared minus 2x e to the power y minus 1. And this is a quadratic equation for e to the power y. But we know how to solve quadratic equations. We learned this in school. The solution to ar squared plus br plus c, as we learn in school, is minus b plus or minus square root of b squared minus 4ac over 2a. So what is a, b, and c for us? A is 1. B is minus 2x. And c is minus 1. Put these in. E to the power y is 2x, because that's minus b, plus or minus the square root of b squared, so minus 2x all squared, minus 4ac, that's plus 4, divided by 2a, so just divided by 2. And this simplifies down to x is equal to plus or minus square root of x squared plus 1. But do we want plus here or do we want minus here? Well, remember, we need this to be equal to e to the power y, and e to the power y is always greater than 0. If we chose a minus sign here, we would get a negative number. So that means we need to have a plus just here. So far we've got e to the power y is equal to x plus the square root of x squared plus 1, and we want y. So we'll take the natural logarithm of both sides. Inverse sine of x, which is the same as we started with saying it was y, is then ln of x plus the square root of x squared plus 1. There's a similar formula for inverse cosh, but I'm going to leave that one for you to prove. The only difference here is there's a minus sign instead of a plus. So if you did exactly the same calculation that I did, but starting with cosh instead, you'll see that the calculation is pretty much the same, except that you end up with a minus sign just there. Let's talk about the derivatives of the inverse hyperbolic functions. We're going to be using the formula in the yellow box, the derivative of the inverse function formula, with f of x is cosh x and f inverse of x is arc cosh x, or inverse cosh of x. And remember, the derivative of cosh is sine. So we have that the derivative of inverse cosh is 1 divided by f prime sine of arc cosh x. We had an identity for cosh and sine. Remember, cosh squared minus sine squared is equal to 1. Using that, we have the same as 1 divided by the square root of cosh squared arc cosh x minus 1. That's 1 divided by the square root of x squared minus 1. The other 5 are similar, so I'm not going to prove them. I'm just going to tell you the 6 different derivative formulae, which again you have on your formula sheet. The derivative of arcsine is 1 over the square root of 1 plus x squared. The derivative of arc cosh is 1 over the square root of x squared minus 1, as long as x is greater than 1. The derivative of arc fan x is 1 over 1 minus x squared, as long as the absolute value of x is less than 1. The derivative of arc cof x is the same thing, 1 over 1 minus x squared, but this is true for absolute value of x greater than 1. The derivative of inverse, I had to write inverse here because I ran out of space. Inverse sec x is minus 1 over x square root of 1 minus x squared, as long as x is between 0 and 1. And the derivative of cosec, so inverse cosec x, is minus 1 over absolute value of x square root of 1 minus x squared, as long as x is not 0. As soon as you have these 6 derivative formulae, you could then write down the 5 integral formulae just by going backwards. So for example, let's just look at the first line. If the derivative of arcsine is 1 over the square root of 1 plus x squared, then that tells us that the integral of dx over the square root of a squared plus x squared is inverse sine of x over a plus c. And so on. I'll leave the others for you to look at later. In the exam, I will give you the derivative formulae, but I will not give you the integral formulae because the formulae are basically the same. If you know the derivative formulae, then you should be able to write down the integral formula as well. So practice that, make sure you're familiar with how you can know the derivative formula and then use that to find the integral formula. For example, and this is the sort of question I might give you, calculate the integral from 0 to 1 of 2 dx over the square root of 3 plus 4x squared. And that sort of looks like what we have in the yellow box at the top. Not exactly. We have a 4x squared instead of an x squared. So the first thing to do is to do a substitution. We're going to let u be equal to 2x, and then we're going to be using the formula in the yellow box with a is the square root of 3. The indefinite integral first is the integral of du over the square root of a squared plus u squared. So that's inverse sine of u over a plus c, or inverse sine of 2x over root 3 plus c. And then the definite integral is inverse sine of 2x over root 3 calculated at 1 and 0. Which is inverse sine of 2 over root 3 minus inverse sine of 0. The second one is 0, so this is inverse sine of 2 over root 3. So let me just scribble on the page. If I cross this h out, and if I change this plus sign to a minus sign, then we get the formula that we had earlier. The integral of dx over the square root of a squared minus x squared is inverse sine of x over a plus c. But if we have a plus, then we have inverse hyperbolic sine instead of inverse sine. How do you know which one to use? You have to look carefully at the formula page, and that will be the test. This problem has a plus at the bottom, so we're using the formula with inverse sine. If we did the same example but with a minus in, the calculation would be similar, except we would be using inverse sine. And that brings me to the end of this course. Are there any questions?